All right, let's go ahead and get started with this example 7.4. So we have this object that is moving along a parabolic path, and it has some kind of force acting on it, and we want to find the work done by this force. Okay, so the first thing we want to do is write out our path here. And it's described as this equation here. Okay. And since we'll be looking at our work done, remember that our initial work equation was as so. Force times, F dotted into dr. Okay. So we can use this understanding, okay, in order to solve this problem, okay? So what we'll do is we'll go ahead and take our derivative of this equation. That way we have it in terms as dr, okay? So we'll say dy is equal to 1/2, and it'll be times 2x, and that's 1/m. Okay, so our dy now is x, and we will keep the units here. Okay, all right, so now what we can do is we can plug it into this equation here. So dw is equal to F, which is, I'm going to go ahead and not look at our units for a minute here. Okay, it'll make it a little bit simpler. So I'm going to say 5y I hat plus 10x j hat. Okay, now this is going to be dotted into dr bar, which is x, okay, and that's going to be I hat plus dy j hat. Okay, and we're again just kind of leaving this aside for a moment. Oh, this should say dx as well. Sorry about that. And again, this is the same as we had before, where we had f sub x I hat plus f sub y j hat dotting into dx I hat plus dy j hat. Okay, so this is the same form as that. Okay, so let's go ahead and take this. So we'll have 5y dx plus 10x dy. Okay. Now what we'll do is, using these two equations here, we'll plug in our y value and our dy value, okay, to make it all in terms of x. Okay, so let's take that. We'll say 10 times y, which is 0.5. Oops, this should have been 5. My bad. Let me erase that real quick. If I can do it really quick. Eraser, boom. Okay, so this will be 5 times 0.5 x squared dx, okay, plus 10x times dy, which is x dx. Okay. All right. So now we have, if I write it again, dw equals 5 times 0.5, which is 2.5, x squared dx plus 10x squared dx. Or we can say 12.5 x squared dx, okay? So this is our derivative of the work. If we want to take our integral, okay, that is the next step here. So now the work from a to b will be the integral. Again, it's the same as the integral here. Okay, so we'll just have to take the integral from a to b, which is 0, 0 to 2 and 2. And we're just looking at the x component now, so we can just say 0 to 2, okay, of 12.5 x squared dx. Okay, so hopefully this setup made sense. Now we can go ahead and solve. We'll get 12.5 times x cubed over 3 from 0 to 2, which the 0 will give us nothing. So we'll have 12.5 times 2 cubed over 3. So 2 cubed is 8 times 12.5 divided by 3, and we get 33. And this is going to be in joules, and we can make sure of that. So let's see. Should be in joules or Newton meter. Okay, so this, let's see. This was in meter inverse. What was this guy in? Meter inverse. So then this should have been in, because this was also Newton per meter. Newton per meter. Right? Yep. Okay. And so this was in meters, I'm sorry, Newton per meter squared. So this was in Newton per meter squared. And then, yeah, this gives us Newton meters. Yeah. Because then we took an integral, then we have meters to the cubed, okay? And so we have meters to the cubed divided by meters squared, and we get Newton meter, okay? So there we have it. Okay, we're going to talk about one last topic in work, and that is going to be work done by force exerted by a spring. Okay, so this is going to be a spring force, which is F equals negative K delta X bar. Okay, where K is our spring constant here. Spring constant. And our delta X is going to be our change in our X position. Okay, so our spring, our work done by a force exerted by a spring is going to be equal to the integral from a to b, okay, of our force, F sub x dx, okay? And then we can plug that guy in, and we get negative k integral from a to b, x dx. And solving for that, we eventually get that our work exerted by a force by a spring is equal to 1/2 k, and then times x b squared minus x at a squared. Okay, so this is going to be our formula here. Okay, and we can see it in this diagram what we're looking at. Okay, so this is our equilibrium position. And This is, so basically it's at rest, right? There's no strain on it or anything. And then we pull the spring, some delta X, okay? And so then it has a force of negative K delta X, okay? And then if we compress it, again, we have the same force here. If we're using the same displacement, okay? So let's go ahead and look at an example. So this is example 7.5. It states that a perfectly elastic spring requires 0.54 joules of work to stretch 6 centimeters from its equilibrium position. Okay. The first question is, what is its spring constant, K? So we'll use this formula here. We'll say work is equal to negative 1/2 K xb squared, whoops, should have been a minus, xb squared minus xa squared. Okay, and we have our work. We have some stretching point. Okay, and we need to find K, so let's go ahead and say K then is going to be equal to negative 2 times the work, okay, divided by xb squared minus xa squared. Okay, just doing a bit of algebra there. So we have 2 times 0.54 joules divided by xb squared, and that's going to be our final point, right? So that'll be 6 centimeters squared minus its equilibrium position. So our equilibrium is going to be 0 centimeters squared. Whoops. Should go like that. There we go. Okay. So our spring constant is going to be negative. We have 2 times 0.54 divided by 6 squared, or 36. So this gives us a spring constant of 0.03. Okay? And this is joules per centimeter squared, which is kind of a weird unit, but that's okay for this one. Okay? All right, so now we want to know, if we know our spring constant, how much work is required to stretch it out an additional 6 centimeters. So we stretched it the first time to 6 centimeters. So if we stretch it out an additional 6, that'll mean that x sub b will be 12 centimeters now, right? Because it's 6 centimeters plus 6 centimeters. Okay. So we want to know what the work done would be. So we have work is equal to negative 1/2 times k times x sub b squared minus x sub a squared. And this is from our equilibrium position again. Okay, so equilibrium is x sub a equals 0 centimeters. Okay, so we have negative 1/2 times our spring constant, negative 0.03 joules per centimeter squared, times x sub b, which is now 12 centimeters, minus 0 centimeters. So that is our starting position. Okay, so now we can go ahead and put that into our calculator. And we get that our work done is now 2.16 joules. Okay, so this is now the amount of work required to stretch it an additional 6 centimeters. We'll see you in the next